Hello everyone, my name is Maryam Saberi and I'm a postdoctoral researcher at University of Oslo. Today in this presentation, I'm going to talk about the life cycle of stars, and then I will shortly go through radio astronomy and I will show you how observations at radio bands can help us to understand the stellar evolution better. To start our journey, I will start from a star's birth. Here you see an image of Orion constellation, as we can see with our naked eyes in a dark night. But if we look at telescope to look at Orion, we can see a giant nebula right in the belt of Orion, which is called Horsehead Nebula. Here you see a better image of Horsehead Nebula, which is taken with the Hubble Space Telescope. Nebulas are giant molecular clouds, mostly contains hydrogen and dust particles. And all the stars that we see in the sky are born from nebulas similar to this. So everything starts with a giant molecular cloud in which the dust and gas particles are slowly come together to form a star. Now I want to show you a short movie that shows how stars can be formed from this nebula. As you can see here, over the time, the dust and gas particles are come together under the attractive force of gravity. And over the time, these clouds get thicker to form this giant spinning disk. In the center, the gravity is stronger, so it can attract more dust into a super dense and super hot ball in the center until the pressure heats up and strong jets can launch from the center and accelerate the materials away, as you can see here. As the gravity gets stronger in the center, the protostar gets more dense and it gets smaller, hotter, and brighter, until the temperature in the center reached to 15 million Kelvin. At this temperature, the hydrogen nuclei can fuse together and produce the helium atoms. And in this process, a huge amount of energy can release. And this is like the birth of a star from a protostar. Yeah. Yeah, this is how stars are born from nebulae. And now we can call it a newborn star, or more precisely, a main sequence star. In the main sequence phase, the star is stable because the inward pressure due to gravity is perfectly balanced with outward pressure due to nucleosynthesis. And stars stay most of their lifetimes in this phase of evolution, as our sun is now in this phase of evolution. The main stars stay in this phase of evolution until most of the hydrogen supply in the core will be fused to helium. So when there is no more hydrogen supply in the core, we don't have any nuclear reaction anymore. So the gravity takes over. The gravity contracts the core of the star. As the star shrinks, it gets hotter until the temperature rises again, that we can have a new nuclear reaction. We can have new nuclear reaction to begin. And at this phase, the outer envelope starts to expand, and the star will evolve to a red giant phase. So in the red giant phase, we have a new cycle of nuclear reaction, and it depends on the mass of the star. Here you can see different nuclear reaction and the duration of each reaction and the temperatures that are needed for each reaction. As I said before, to fuse a hydrogen and make helium, we only need 15 million Kelvin. However, to fuse helium to carbon, we need 100 million Kelvin. And this is the last nuclear cycle that Sun can go through. In order to continue and fuse heavier elements like carbon, we need stars with higher mass. Only stars with, which have mass of more than 25 times of our Sun, they can go through all these cycles. And they can even fuse silicon to make iron. This process needs approximately 3 billion Kelvin. And it's very quick. It only takes 1 day. As you can see here, stars are factories that can produce all heavy elements in the universe. If we look at the periodic table, only hydrogen and helium are the species that really come from the Big Bang, and all other heavier elements they are producing inside the stars either due to nuclear reaction or when the stars explode, if they are massive enough to explode. As you can see here with the color code, for example, the species that are marked with green, they are coming from dying low-mass stars. And like the yellow ones coming from exploding massive stars. This means that basically everything that our bodies are made of, or everything that we see around us, they all come from inside the stars. Another important point that I would like to make about the stellar evolution is that the life path of stars and the age of them depends on their mass. So their mass is a determining factor that determines how long they can live and which evolutionary path they can take. Here you can see two evolutionary paths. The upper one shows the evolutionary path for low and intermediate mass stars, including our Sun. And the lower one shows the evolutionary path for high mass stars. As you can see here, for low to intermediate mass stars, from low to intermediate, I mean from 0.8 solar mass up to 8 solar mass. After the main sequence, the star will enter the red giant phase, which is pretty unstable and a short phase of evolution. And eventually start to lose its mass and create this pretty planetary nebulae. And over the time, this layer of gas and dust will expel to the space, and this leaves behind a white dwarf. Why we call it a white dwarf? Because they are pretty small and very shiny. And over the time, white dwarf emits its energy, and it will become a black dwarf because it has no more energy to emit in space. For high mass stars, they have a shorter lifetime because they burn the fuel in their core much more faster because the temperature is much more higher in the center. And after the main sequence phase, they will become red supergiant. They are really big. And the red supergiant phase is also very unstable, and it eventually red supergiants explode as supernovae. Supernovae are the most explosive phenomena that can happen in space. And what happens after supernovae explosion again depends on the stellar mass. For high mass stars, they will become neutron star, and for very high mass stars, they will become black holes. Neutron stars, we call it neutron because all electron and proton come together, combine, and makes neutrons, so they contain only neutron. And black holes are like tiny holes in space, that they are super dense, and the gravity is very high that nothing can pass through, even the light. In a few, a bit later, I'm going to compare their density to give you a better feeling about how dense these are. Before looking at that, I would like to show you the life cycle of our Sun. Our sun was born approximately 4.6 billion years ago from a nebula, like I showed you before, and it has enough fuel in its center to live like this for another 5 billion years. And after that, it's gonna be a red supergiant, and finally a white dwarf. When our sun goes to the red giant phase, its outer radius is gonna expand to somewhere approximately 1 AU, which is the average distance of Sun and Earth now. So there will be no Earth anymore when our Sun becomes a red giant star. Now to compare, to see how dense the stellar remnant are after the death, we can look at this is relative size of Earth and Sun. When our sun becomes a white dwarf, all the mass is gonna shrink into a small ball with a radius of Earth. So all the mass is gonna shrink into a ball with radius of only 5,800 kilometers. And neutron stars are even more dense. They are heavier than white dwarfs, and they are gonna shrink into a ball with radius of only 10 to 20 kilometers. So you can imagine how dense they are. And it's gonna be worse for black holes. Black holes, the radius of them are approximately 4 kilometers. So they are super dense, and the physics inside them is not known because nothing can pass through, even the light. Now I would like to change the topic a little bit and tell you how we study stars and stellar evolution. Essentially, all the information that we get from space are coming from the electromagnetic spectrum. And here you can see this tiny strip, which is the visible light. This is the only part that human eyes are capable of seeing. But to look at other part of the electromagnetic magnetic spectrum, we need to use either space-based telescopes or ground-based telescopes. But you may wonder why we need to look at through the whole electromagnetic spectrum. I can give you an example. Here we see a Whirlpool. Here we see the Whirlpool galaxy. This image is taken with an optical telescope. And here you have an image of the same galaxy at different wavelength, from radio to X-ray. As you can see here at radio, when we look at the galaxy at radio, we can observe the distribution of cold gas, which is not visible at optical. When we use infrared observation, we can look at cool stars. Cool stars, since they are dusty, they are not visible at optical wavelength. And in optical, we mostly look at a star similar to our sun. Going to higher to high energy part of the spectrum, like ultraviolet, we can look at distribution of hot stars. And if we want to look at the hot gas and ionized gas, we need to do X-ray observation. So as you can see here, in order to see all the components of a galaxy, we need to do multi-wavelength observation. Otherwise, we're gonna lose some part. So astronomers, depending on their science case, they are using observation at different wavelengths, and sometimes we need to combine them to get a better picture of the galaxy. Now, since I'm a radio astronomer, I'm going to talk a little bit about radio astronomy. Radio astronomy is a relatively new branch in astronomy, which began in 1931 when Carl Jansky accidentally discovered the radio emission from Milky Way. He was an astronomer, he was an engineer who was working for a Bell Telephone Company in the US, and he accidentally discovered that some noises And this is a picture of him and the antenna that he used to detect this radio emission. And by continuing his observation, he realized that the source of this noise that he's detecting is celestial and is not from the Earth. And this was the beginning of radio astronomy. But nowadays, we are not using like antennas like this. The new generation of radio telescopes are mostly look like this. We are using antenna. One problem that astronomers was faced at the beginning of radio astronomy was the resolution of observations. The resolution of observations is proportional to lambda over d. We can have it with this simple formula, where lambda is the wavelength of the wave that we are going to observe, and d is the diameter of the telescope. Now, to give you some feeling about the resolution of observation, imagine that we want to have the same resolution as we have with optical telescope. We have an optical telescope and we have a radio telescope. And if our optical telescope have a diameter of only 1 meter, and we are going to observe a wave at 500 nanometer, if we want to get the same resolution as we have in optical, in radio, and we want to observe radiation with wavelength of 5 centimeter, if we put these numbers in this simple formula, this tells us that we need a radio telescope with a diameter of 10,000 meters, which is impossible to build from engineering point of view and from economical point of view. So what should we do to increase the resolution of observations? You may wonder how big is the largest telescope that we have in radio. The largest radio telescope has a 500 meter diameter, which was recently built in China. But this is a giant telescope, but this is still far away to get the same resolution as we have in optical. To solve this, astronomers use a technique which is called interferometry technique. This is very smart technique to use actually. In interferometry technique, rather than making a giant antenna, we are making two small antenna and we place them far away from each other. And now, these two antennas, they're observing the same source at the same time, and then we combine their signal and with interferometry, now the distance between two antennas goes in this formula. So in this, with this technique, and as we increase the number of antennas, we can get a better and more high-resolution observations. This technique, for the first time, was used in 1940s, and using these techniques, we can get a very high resolution observation that we can see all the structures in the stars and even the galaxies. We can distinguish all the components, which is pretty amazing. I'm going to show you some results of the interferometry technique. Atacama large millimeter array is currently the most powerful radio antenna, which contains 66 antenna, and it's located at the altitude of 5,100 meters in the Atacama Desert at Chile. This is the most expensive telescope that we have now, and as you can see here, these cars were just made to transport the antenna, because these antennas can be moved to change the resolution of the observations. And this is for astronomers, it's very competitive and hard to get time to observe with this telescope. And here I would like to show you some observations that are taken with ALMA from stars at different evolutionary stage. The first image that you can see here, this is an image of a planet forming disk around the star HL Tau. You can see that it's pretty amazing that we can resolve all this structure, the gas and dust structure around the stars, and this helps us to understand the planet formation around the star, at which radius planets can form, and how many planets can be formed around the star. Here you see another image of ALMA observation from our sun. ALMA observation of sun is relatively new and is still under progress. When we look at the sun with ALMA, we can directly measure the temperature in the upper chromosphere. And here at University of Oslo, one of the biggest and leading groups that are working in the ALMA observation of sun actually is located here at Roseland Center for Solar Physics. This figure here, the down corner, this is an ALMA observation of a dying star. This is a red giant star, and this is a carbon monoxide map around the star. This was the first time that ALMA observation shows us this spiral pattern in the outflow of this red giant, which indicates that this is not a single star. It has actually a binary companion that they rotate, and this rotation makes this molecular gas to look like a spiral. In addition to imaging the stars, we can also observe different molecular components around cool stars. Here you see spectroscopic observations of two red giants again. As you can see here, we can observe different molecules at different wavelengths with ALMA, and this helps us to understand the chemical composition of this outflow around dying stars, which is pretty new, and we can precisely determine the molecular distribution and how much of each molecule is there with very high accuracy. Okay, I would like to finish my presentation here. Thanks for your attention.